In this tutorial, we're going to define the trigonometric ratios. Trigonometric ratios are probably words that you've already come across. They are the sine, the cosine, the tangent, and then there are three others known as the secant, the cosecant, and the cotangent. Now the sine, the cosine, and the tangent are the ones we're going to look at here. And before we do anything else, we're going to show you exactly what is meant by those three terms. Okay, so let's start by a bit of compass construction. I'm going to construct an equilateral triangle. So I'm going to draw a line down here, and from a straight line you can just stretch your compasses. So if I put my compass at this point, stretch it to exactly the length of the triangle, draw an arc from here, and then put my compasses at this point and draw an arc from here. So where they cross, I'll get it must be equidistant, so it's going to be the same distance there, and up to the point here. All sides now are equal, so we've created an equilateral triangle. Okay, so in an equilateral triangle, in any triangle, the sides, the angles rather, must sum to 180 degrees. So if there are three angles, then each angle must be 60 degrees. So this angle here, for example, let's label 60 degrees. Okay. So that's one of my angles done. The other angle I want to look at is 30 degrees. So if I bisect the equilateral triangle now, draw a line across here, then this angle here must be 30 degrees. Let's draw a degree sign a little neater. Okay, there we go, a bit better. And here, well, we don't have to draw. We don't have to write 90. We just have to do the right angle symbol, and so that tells us that this must be 90 degrees. And as a quick check, 30 plus 60 makes 90, plus another 90, 180 degrees then inside this smaller right angled triangle now. So a sine, which comes from the word sinus, the root of that is often identified as bowstring. So sinus means bowstring, and we can see why that might have developed as an idea. You can see this as a bow. In fact, if I just imagine this side here as the bow, here's the arrow, here's the string, I suppose. Anyway, something like that is the reason why we call it sine. And all that sine means, all it means, is one side over another side, the ratio of one side to another side, and sine means the ratio specifically of the opposite side to the angle over the hypotenuse. And the hypotenuse is the longest side of any right angled triangle. It's the side opposite the right angle. So sine is always the opposite side over that hypotenuse, over the longest side. And whatever size this gets, this triangle, that ratio will always be the same, and that's why it's such a useful thing to identify these ratios. If the angle is the same, the ratio will always be the same, however much we stretch or shrink this triangle. Okay, but what exactly is then that ratio of this side to this side? Well, if I look at the measure of the sides, it depends on what I set one of the sides to. I'm going to set this side to a length of 2. Okay, so if this was a measure of 2, then all the sides must measure 2, and so half of that side, in other words this side of the right angled triangle, is going to measure 1. So the ratio of 30 degrees for any triangle is simply 1 divided by 2, in other words 1/2. So let's write that down. That's our first value that we've discovered. The sine of 30 degrees, if we're measuring in degrees, is equal to 1/2 or 0.5. Okay, so we don't always need to reach for the calculator. There are some angles, like the sine of 30, that we can calculate and perhaps memorize simply by thinking of this 30, 60, 90 triangle. Now, why don't we try and calculate now the cosine? So cosine simply means the complementary sign, or the complement of the sine, so it's sort of the other one. So we're going to find the cosine of 30 degrees. Okay, so the cosine, we can just shorten it to cos, the cosine of 30 degrees. And what would that be? Well, the complementary sign is, again, we use the hypotenuse, that's the sort of principal side, but this time we're looking at the adjacent side, not the opposite, the one that's next to the angle. And the cosine is always the adjacent side over the hypotenuse. So the adjacent side, we don't know what the length of that is. However, we can find it out using Pythagoras. So let's now try and find the length of this side. Well, unlike in a previous video where we used Pythagorean triples, we're going to find that this doesn't come to a nice neat integer. So what is the length of this side? It's well worth discovering and memorizing, because it's very easy to remember when we've found out the pattern. So let's use Pythagoras. So Pythagoras says that the square on the hypotenuse, so 2 squared, so let's jot it down here, 2 squared, equals the sum of the squares on the other two sides. So equals 1 squared then, plus the side we want to find out. Let's for the moment call it x. Okay, so x squared, 1 squared plus x squared equals the square on the hypotenuse. So now if we rearrange this, we get x squared equals 2 squared minus 1 squared. Well, 2 squared is 4, and 1 squared is 1, so that's 4 minus 1, which is 3. So this side here must be the square root of 3, which is not a rational number. In other words, if we write it as a decimal, the decimal, after the decimal point, the digits will go on and on forever. And so it's a convention, and a very useful convention in trigonometry and elsewhere in mathematics, to simply write square root of 3, which we call a surd, or root 3. So this side here, the length of this side is root 3. So we had a 3, 4, 5 triangle, and a 5, 12, 13, and other Pythagorean triples that we thought in a previous video might be good to remember. A really useful one to remember is in fact one that involves a surd, and it's this triangle here. A 1, 2, root 3 triangle. A 1, 2, root 3 triangle will always give you, if it's a right angle, well, it will always be a right angle, will always give you a right angle then, and 30 degrees in the other corner, and 60 degrees up here. So it will always give you 30, 60, and 90 degrees. So that's a useful thing to remember. And once we've memorized this triangle and remembered this triple, if you like, not a Pythagorean triple, but this triple 1, 2, root 3, then we've got a useful way of remembering all sorts of trigonometric ratios. So here we've got the cosine now of 30 degrees. So 30 degrees, the cosine is the adjacent side over the hypotenuse. So the adjacent side is root 3. So let's write down root 3. And the hypotenuse is 2. So that's root 3 over 2. And if you want to change it to a decimal, that's approximately equal to, so we can write approximately equal to 1.73 is a good approximation, or a fair approximation of root 3 divided by 2 then, which equals roughly 0.865. But if we want to keep it in exact form with no estimation at all, then we stick to root 3 over 2. Okay, let's now find the sine of 60 degrees, so of this angle here. So 60 degrees is up at the top here. The opposite now is root 3. The hypotenuse is 2, so opposite over hypotenuse gives you the sine. So again, the sine of 60 is root 3 over 2. And that's approximately equal to, as we've seen, 0.865. So nice and easy. And something perhaps to remember is that the cosine of 30 degrees equals the sine of 60 degrees. Let's have a look now at finally the cosine then of 60 degrees. So again, looking at our 1, 2, root 3 triangle, the cosine is the adjacent side now over the hypotenuse. The adjacent side is 1, the hypotenuse is 2, so we've got 1 over 2. And that's not approximately, but exactly equal to 0.5. So we've got 4 values there then for the trigonometric ratios in the 1, 2, root 3 triangle. In other words, in connection with the angles 30 degrees and 60 degrees. Now the other trigonometric ratio that we mentioned is the tan. So let's just finish this off by writing the tan or tangent, and we'll see later on why it's called a tangent, but it's to do with circles again, and it's to do with a tangent to the circle having some sort of relationship with this ratio. So again, we can abbreviate this by simply writing tan. So let's ask ourselves what the tan of 30 degrees is. Again, our 1, 2, root 3 triangle, very useful. 30 degrees, the tangent is the other ratio, where we're not going to use the hypotenuse, so it must be just the opposite over the adjacent, And that's going to be the 1 here then over root 3. So 1 over root 3. Now, something that we tend to do is not leave a surd in the denominator, so we don't like this root 3 in the denominator. So if you multiply the numerator and the denominator both by root 3, so in other words root 3 times 1 and root 3 times root 3, you can rearrange this in a way to make 1 times root 3 is root 3, and root 3 times root 3 will give you 3. So 1 over root 3 is exactly the same as root 3 over 3, and you'll often see it as root 3 over 3. And that's approximately equal to what? Well, we had 1.73 as a reasonable approximation of root 3, divided by 3 then this time, and that's going to give me roughly 0.58. So tan of 30 is roughly 0.58, but in exact form, root 3 over 3. Okay, let's now finally look at the tan of 60 degrees. So again, it's opposite, which is root 3, divided by the adjacent, which adjacent means next to, so next to the 60 we've got 1, so divided by 1. In other words, it's root 3. And that, as we've seen, is approximately equal to 1.73. So these tangents sometimes they don't have to be less than 1. Sine and a cosine is always 1 or less. Tangent, or between 0 and 1 I should say, a tangent is often over 1, and so we've got 1.73. Okay, fantastic. Let's now look at finally a 45-degree angle. Okay, so to draw 45 degrees, I'm going to again draw a straight line here, 45-degree angle. And I could just use my squares and draw along here, but you can bisect the angle using compasses. We'll look at that in more detail in a different video, so I'm going to just use my compasses here and draw an angle here, and from this end draw an angle. Okay, draw an angle from down here now. There we go. And where they cross gives me exactly 90 degrees. So if I draw up exactly the measure of this side here, I will get a 90-degree angle here, a perpendicular to this vertical, a perpendicular that's exactly 90 degrees, and because they're equal measure, when I join them together, it makes exactly 45 degrees. So here we've got a 45-degree triangle then. So if I label, that's not very well drawn, let's have another go. So if I label the smaller angles 45 degrees, 45 degrees, let's use the colour pen that we used before. Okay. So 45 degrees in that corner, 45 degrees in that corner, and this of course is 90 degrees, a right angle. Okay, so let's continue with our exploration of these trigonometric ratios, but this time in the 45-45 triangle. So let's start with sine. What's the sine then on 45 degrees? Well, again, if I set the hypotenuse to be the same here, in other words 2, then this side length here, well, what's that going to be? It's not quite 1, it's more than 1, but it's less than 2. Once again, let's use Pythagoras. So by Pythagoras we know that the square on the hypotenuse, so that's 2 squared, is equal to, well, what have we got? Let's call this y, and this angle z temporarily. We've got z squared, or y squared, let's do z squared first, z squared plus y squared. But we also know that z equals y. So instead of y squared, we can just write z once again. Okay. So y squared must be the same as z squared. Okay. So let's go for this side here then, find out what z is. So first of all, let's simplify this. So we've now got 2z squareds. So if we add those together, we'll have 2 of them. So we can write 2z squared is equal to 2 squared, which is 4. Okay. So z squared must be 4 divided by 2. If I divide both sides by 2, I get 4 divided by 2 equals 2. So z must be square root of 2. In other words, this side here is root 2. So again, best to keep it in surd form rather than actually do the square rooting on a calculator and finding the decimal. Keep it in surd form, otherwise we introduce inaccuracies. So in exact form, both these side lengths must be root 2. So we're now in a position to work out the sine of 45 degrees. Sine of 45 degrees is equal to what? Well, opposite, if we use this angle here, opposite, which is root 2, divided by the hypotenuse, which is 2. So sine of 45 is root 2 over 2. What about the cosine, the complementary sine of 45 degrees? Okay, well, we've now got the adjacent over the hypotenuse, but in this case the adjacent is the same as the opposite. So the sine of 45 degrees is also root 2 over 2, which means, just as we found here that the cosine of 30 equaled the sine of 60, and in fact that the sine of 30 was equal to the cosine of 60, we've got a similar pairing here. We've got the sine of 45 degrees is equal to the cosine of 45 degrees. They're exactly the same. So there's two more trigonometric ratios, and these are the ratios that are well worth learning and remembering, and try and remember them in exact form, because as soon as you start getting into the decimals you introduce inaccuracies, at least when you've got these surds involved. So finally, let's find the tan of 45 degrees. So the tan of 45 degrees is going to be what? So if again I look at this top angle here, 45 degrees, the tan is always the opposite over the adjacent, so not involving the hypotenuse. The opposite is root 2, so root 2. And the adjacent, the side next to the angle, the adjacent, is also root 2. So we've got something divided by itself. In other words, that must equal 1. So root 2 divided by root 2 simplifies just to 1. So the tan of 45 is 1. And again, something very easy to learn and remember. Okay. Now, so far we haven't said why the trigonometric ratios are so useful. So let's have a go at that in this last part. We've got two problems here, 1, 2, 3. And problem 1 gives us a 45-degree triangle, so we know that this is going to be in the ratio 2 root 2 root 2. But we've been given a side length of 3, so we're going to work with this 3, and we've got 45 degrees. In the second situation, we've got a 30-degree angle here, so we know that this is a 1, 2, root 3 triangle, but we've got a side length now of 4. And in the third problem here, we've got, again, it must be a 1, 2, root 3 triangle, but the key thing is that we've got an angle here, 60 degrees, and just one side. So again, we're going to use trigonometric ratios to fill in the missing sides. Okay, let's start with problem 1 then. So with problem 1, we've got, well, we know that we know we've got the opposite to this angle here. Of course, we've got another 45 degree here, and we know that this is 3, but we're going to just work with this angle 45. So we've got an opposite to the angle. We've got 3. And let's say we're trying to find this side length here. We'll call it x. Okay. So we need to now form an equation and then solve the equation to find out what x equals. So we use the trigonometric ratios to form an equation. And it's a good idea just to jot down something called SOHCAHTOA. SOHCAHTOA is a little mnemonic. It just helps you remember that the sine is opposite over hypotenuse. The cosine, well, that's adjacent over hypotenuse. And the tangent, that's the one that's opposite over adjacent. So jotting that down is a really good tip. And in this case, what have we got? Well, we've got an opposite and a hypotenuse. So identify first the sides that you've got. We've got an opposite over hypotenuse. So for example, we wouldn't want to choose tan. And if it's an opposite, we can see using SOHCAHTOA that we're going to use the sine function, not the cosine. The adjacent is this side length here. We could use that because we know that's 3, but we're going to use this one, which is opposite over the hypotenuse. So let's go ahead and solve our problem. So what we do is we write down what we know so that it forms an equation. So we know that the sine of 45 degrees equals the opposite over the hypotenuse. Okay, so the opposite is 3, so we write down 3. And the hypotenuse is this missing side we're trying to find, so it's x. So we write down x. Now we want to solve this equation, and to do that we need to rearrange the equation. So if you're not sure about rearranging equations, then you need to go back and look at how we do that. But basically I want to get x on the left hand side, and I want to get this sine 45 over on the right. We can immediately fill in sine 45, in fact, so let's do that straight away. We can say that sine of 45 is, using the exact form, root 2 over 2. The advantage of using the exact form, remember, is we don't introduce inaccuracies. We're not working with long decimals. So root 2 over 2 is 3 over x. And we can now just flip this over both sides so that we've now got this x over 3 must equal 2 over root 2. Okay, now to get x on its own, we just multiply both sides by 3. That leaves us with x equals, so 2 times 3, in other words 6 over root 2. And we're nearly there, but remember we have to rationalise. It's called rationalise our denominator here, which means we just get rid of this root 2 in the denominator. We do that by multiplying by root 2 over 2. Root 2 over root 2, sorry, because root 2 over root 2 is just 1, but what it'll do is it'll remove the surd in the denominator. So we've now got on the top 6 root 2 in the numerator, and in the denominator here we've got root 2 times root 2. Well, root 2 times root 2 is root 2 squared, so it's just 2. So the answer must be 6 divided by 2, 3 root 2. And again, we could work this out to give a decimal, maybe to a couple of decimal places, but if we want it in exact form, we just leave it as 3 root 2. Okay, now we can do a quick check here. So let's just do a quick check. If we check this, let's do this here, check by Pythagoras, we know that this is 3, so x squared must be, so the square on the hypotenuse must be the square, the sum of the squares on the other two sides. Well, that's 3 squared plus another 3 squared, 2 3 squared you could say. In other words, 2 3 squareds makes, well, 3 squared is 9, so 9 plus 9 makes 18. So x squared is 18, and if x squared is 18, then x, so therefore x must be square root of 18. Well, surds can be split up to simplify them because we haven't yet got 3 root 2. So what you can do is you can rewrite this root 9 times 2, because 9 times 2 is 18. So now we can split this up and say x equals, gets a bit complicated, but this is a useful check and after a while not too difficult. We've now got root 9 times root 2, and the root of 9 is 3, so that's going to be 3 root 2, so this must be correct. Okay, now we could check this one by Pythagoras, but problem 2, we don't have that option available because we just don't know what this side is here. Let's decide which of these two sides. We could perhaps get both, but let's start with this one, y. In fact, maybe just to save time, maybe we'll just leave this other side, and that would be a follow-up exercise that you could do just to give yourself a bit more practice. But we're going to aim for y. So problem 2, we need to first of all look at our SOHCAHTOA mnemonic and figure out which of the two sides we're going to be using. So here we are in the 30-degree angle. We're looking across from 30 degrees, so this must be the opposite side. Okay, so if we write down sine of 30 degrees, and look up here, it's the opposite over the opposite over the hypotenuse. So sine of 30 degrees is 4, that's the opposite side, and the hypotenuse always is longest side opposite the right angle here. So sine of 30 degrees is 4 over y, over the hypotenuse. Okay, and just as before, we can rearrange. In fact, it might be an idea now just to no, let's do what we did before. Sine of 30 degrees, we can change that straight away. Sine of 30 degrees, we know, and a good one to memorize, we know is a half. Keep it as a fraction, won't change it to a decimal, and so we now say that a half is 4 over y. Therefore, y over 4 equals 2 over 1, so 2. So y equals 8. And there is a check we can do here. We ought to remember that this is a 30 degrees and a 60 degrees and a 90 degrees. This is a 1, 2, root 3. So if you remember this 1, 2, root 3, so root 3 would be the adjacent side in this case. The 1, 2 reminds us that the hypotenuse should be double or twice the opposite side here, this side here. So the shorter leg is half of the hypotenuse. So our answer of 8 is twice 4, so our answer must be correct. Okay, finally, let's look at problem 3. So problem 3, we've got a 60-degree angle, so it's a 1, 2, root 3 triangle again. But let's just work with our trigonometric ratios. So we know that let's say the missing side that we're trying to find, let's call it Z, is this one here. So we'll say what of 60 degrees? Which trigonometric function are we going to use? Well, we've got, if we look across from our 60 degrees, we've got an opposite side. And this side here feels like it might be adjacent, but remember the longest side opposite the right angle is in fact the hypotenuse. This is the adjacent side. So this long side here that we've got labelled here is the hypotenuse. So we've got the opposite over the hypotenuse. So once again, we've got the sine function. Sine of 60 degrees. Sine of 60 degrees is the opposite over the hypotenuse. So sine of 60 degrees is Z over 5. Rearranging this, we get sine of 60 degrees is root 3 over 2. So root 3 over 2 must equal Z over 5. And we don't need to swap these over now. We've got just what we need here. We just need to multiply both sides by 5, and we'll get Z equals 5 root 3. So 5 root 3 over 2. And we can leave it at that because the number in the denominator isn't a surd, so we've got 5 halves of root 3. We could rewrite it 5 halves or 2.5 root 3, but I think that's really getting a little bit unnecessary. It's fine to leave it just like this. Okay, again we could get out our calculator and we could find out what that is, but there's no need. Now, just to finish, let's find another one. Let's call this, if we call this Z1, okay, let's find Z2 just to complete this. Now Z2 is the adjacent side, so we've got Z2 is the adjacent, and we've got now a hypotenuse. We could use the opposite, but it's a bit fiddly. I'm going to use the hypotenuse here. So we've got adjacent over hypotenuse. So going back to SOHCAHTOA, we've got cosine is the adjacent over the hypotenuse. So cosine of 60 degrees is the adjacent, which is Z2, over the hypotenuse, which is 5. Okay, multiplying both sides by, so we could rearrange cosine of, let's do that first. We can do it in any order. So in fact, why don't we just multiply both sides by 5 and rewrite this 5 cos 60, because sometimes you'll see this. Maybe not my favourite way of doing it, but Z2 is 5 cosine 6. Therefore, Z2 is 5 times, well, what is the cosine of 60? Cosine of 60 is a half, so it's 5 times a half, or 5 halves. And that makes sense because we know, again, that this is a 1, 2, root 3 triangle. So this side here ought to be half the hypotenuse. So that one's a nice easy one to check. Again, the hypotenuse is twice the small leg in the 1, 2, root 3 triangle. So Z2 equals 5 halves, or 2.5 if you want to change it to a decimal. So this must be correct.